Hi everyone, welcome to Introduction to Geology. I'm Dr. William Patterson. Today we'll be talking about earth materials, in particular focusing on rocks and minerals. Now this is going to be a four-part video series with part 1 coming up next, covering minerals and how they form. Part 2, classes of rock-forming minerals. Part 3, the video will cover physical properties of minerals and what are rocks. The fourth video in the series will be the rock cycle, which includes interactions between the plate tectonic and climate systems, basically how the movement of the Earth's plates generates different suites of rocks and minerals. And then we'll wind up with a little bit on concentration of valuable mineral resources. Now, earth materials consist of minerals such as this one. The name amethyst comes from the Greek methestos, and which means not to be intoxicated. This is based on the belief that if you're consuming alcohol in contact with amethyst, that you will not become intoxicated. And there's a whole bunch of Greek mythology that goes along with this. It's kind of fun to go through, but we're not going to cover it here. Amethyst is a violet variety of quartz that owes its violet color to irradiation. Impurities of iron, in this case iron 3+, and in some cases other transition metals, and the presence of other trace elements result in complex crystal lattice substitutions. The irradiation causes the iron F3+ to replace silicon in the lattice and lose an electron, ultimately forming an iron color center. Treated amethyst or artificial amethyst is created by using gamma radiation or X-ray radiation to damage clear quartz, which we also call rock crystal. We call a bunch of things rock crystal, so it's not really a good name. We're going to blast it with radiation, and this radiation allows iron impurities to seep into the crystal again. In this case, we've doped the crystal surface with iron impurities. And alternatively, exposure to heat partially cancels the irradiation effects, and amethyst generally becomes yellow or even greenish in color. Much of the citrine and caramgorm, or yellow quartz of jewelry, is thought to be burnt amethyst, basically baked amethyst. Earth materials are composed of atoms bound together. Minerals are composed of atoms bonded together and are the building blocks of rocks. Rocks, in turn, are composed of minerals, and those minerals record various geological processes. The formation of those minerals takes place under certain conditions that we can figure out, and therefore we can reconstruct the history of the rock based on what's present. So in this instance, we have an example of pure carbon formed into a diamond. Alternatively, pure carbon formed into the mineral graphite. The only difference here, it's not compositional difference, it's the way the atoms are arranged. They're the exact same atoms arranged differently. The result is different minerals with different characteristics and therefore different histories. Continuing our discussion on minerals, we're going to talk about what are minerals, the structure of matter that ultimately makes up the minerals, the formation of minerals, how these components come together, assemble themselves. Minerals are the building blocks of rocks. Rocks, in turn, are made of one or more minerals. A mineral is a naturally occurring solid crystalline substance, usually inorganic, with a specific chemical composition. This is very important to know. This is the definition of what a mineral is. All of these components are critical to the formation of a mineral.
You see that sign? No shirt, no shoes, no ties.
Right. Learn it. Know it. Live it.
Now, some examples here. These are sulfide minerals, which means they all contain sulfur. We have galena, which is a lead sulfide, chalcopyrite, an iron copper sulfide, sphalerite, a zinc sulfide, molybdenite, a molybdenum sulfide, pyrite, also known as fool's gold, iron sulfide, bornite, a copper iron sulfide, arsenopyrite, an iron arsenic sulfide, and stibnite, an antimony sulfide. So what are minerals? They're naturally occurring. That means they're found in nature. They're created naturally. They're also solid and crystalline. That means atoms are arranged in orderly patterns. They're usually inorganic. not a product of living tissue. Now, there are exceptions. They're very common. Your teeth, for instance, are the mineral apatite, but we're not going to get into that whole diatribe right now. And they have a specific chemical formula or a unique chemical composition that's inherent to that particular mineral or type of mineral. Now, an atom is the smallest unit of an element that retains the physical and chemical properties of that element. Here we have the mighty carbon atom. It's going to consist of an electron cloud and an atomic nucleus. This atomic nucleus consists of protons and neutrons. The electrons form a cloud of moving particles surrounding the nucleus. And the example again here, the carbon atom, if the nucleus was about the size of a football, the electron cloud will be about the size of Michigan Stadium here. The big house holds about 110 to 120,000 people for those of you that don't go to the big house regularly. The carbon atom, again, consists of an atomic nucleus and the electron cloud. This is carbon. The element has 6 electrons and a nucleus of 6 protons and 6 neutrons that have no charge. The electrons have a negative charge and the protons have a positive charge. Again, neutrons are neutral. The structure of matter also includes the production of isotopes. The focus of my career choice as a scientist, deals with isotopes. Now, these are atoms of the same element with different numbers of neutrons. The example shown here is carbon-12, the most common of types of carbon atoms. The vast majority of carbon is carbon-12. There's a couple percent of carbon-13, however. This is a stable isotope. Carbon-12 is a stable isotope. They don't change. They don't break down radioactively. Carbon-14, on the other hand, has 2 electrons more than carbon-12. This is a radiogenic or radioactive element. It does break down radioactively. And this gives us the ability to determine the age of things that are made up of carbon. Chemical reactions are the interactions of the atoms of 2 or more elements in certain fixed proportions. The example shown here is water, or H2O. As a liquid, it forms, this isn't quite right, but it generally forms a mass of 9 molecules or so. It kind of wiggles and flops around. Once the temperature goes down sufficiently, they become organized, and they become organized into a hexagonal crystal structure. So unorganized here as a liquid, very well organized here as a solid. And this solid takes up a little bit more space than this disorganized liquid, so ice takes up more space than liquid water. Another example, a common example, is sodium chloride, which we call table salt, or its mineral name, halite. This is composed of sodium atoms, which are the positive or cations, and chloride ions, which are the negative or anions in this crystal structure. Now, these chemical compounds that form minerals can do so by electron sharing or by electron transfer. In electron sharing, the carbon atoms in a diamond are arranged in a specific way. All of the carbon atoms share their electrons with other carbon atoms, and that takes this form crystallographically. They're little tetrahedrons of carbon all linked together. In electron transfer, one atom gives up an electron to another, or one atom takes an electron from the other. So in this case, our sodium chloride crystal is made up of a sodium atom with 1 electron in the outer shell, and linking up with the chlorine atom has 7 electrons in the outer shell. It wants 8. Sodium wants a complete outer shell as well, so the result is the sodium gives up its electron to give chlorine its perfect electron shell, and sodium now has a perfect outer electron shell as well. When these come together as sodium chloride crystal, they occupy specific places in space. A specific portion of the crystal lattice is given up to chlorides. Another portion of that crystal lattice is specific to sodium. And the result is a cubic crystal. This is cubic in the large crystals shown here. And if we break these down, as we'll see how to do that coming up soon, you get smaller and smaller cubes. until we get down to the atomic level size cubes. So each sodium ion, circled in red here, is going to be surrounded by 6 chloride ions, circled in yellow, and vice versa. How do these minerals form? What causes them to come together? This is the process of crystallization. Atoms come together in the proper proportion and the proper arrangement. Every atom knows its place. Ions can have 2 electrical charges. A cation is a positively charged ion, and an anion is a negatively charged ion. Atomic ions arrange themselves according to charge and size. Here we have some common cations and anions: silicon, aluminum, iron 3+, magnesium, the slightly larger iron 2+, sodium, calcium, and potassium. The anions that are most common in the Earth's crust are oxygen, chloride, and sulfide. Now, these should come together in a specific fashion in a specific mineral. So slow crystallization produces orderly crystals. There's time for the right atoms to assume the right position, to look for a vacancy here. Will this atom fit in this position? If so, it becomes part of the crystal lattice. If crystallization occurs too quickly, it can result in the wrong size ion being incorporated into a growing mineral. What's the outcome there? Well, it's chaos. The ions don't fit properly, so the crystal lattice ends up being distorted or damaged, altered. It makes for a mineral that's easier to break apart. It's more easily dissolved in solution. It's not as stable as a well-organized crystal. So in the structure of minerals, we need to consider the forces of electrical attraction between protons and electrons that hold minerals and other chemical compounds together. They do this via covalent bonding, in which the electrons are shared. Now, we've seen that in diamond and graphite. And you can think of this as kind of a hippie commune, where everything that's mine is yours, and everything that's yours is mine, man. So the hydrogens in this case are sharing the electrons. Everybody has access to everybody else's electrons. Ionic bonds, on the other hand, electrons are transferred. This is the old opposites attract model. And you can say it's like taking candy from a baby. So the chloride ion is going to take an electron from the sodium ion in this case, forming the mineral halite. Over here, we have the mineral ice formed. And lastly, we have metallic bonds. These are bonds in which electrons are shared. They're free to move around the cabin. In metallic bonding, electrons are free to do their thing. Crystallization occurs when atoms of a gas or liquid come together in the proper arrangement to form a solid substance with an orderly three-dimensional array. When do minerals form? When does this magic happen? Well, it happens during the cooling of molten rock, as seen here in Iceland. Liquid magma is coming up through this mid-ocean ridge fissure and reaches the surface, becoming lava, which then spreads out. This lava, being exposed at a much lower temperature of the atmosphere, cools off rapidly and forms a dark-colored igneous rock, which we know as basalt. It can also occur during evaporation of water. Here we have an image from Thailand of people producing sea salt. So when you buy the expensive sea salt in the grocery store or wherever you go to get your sea salt, this is oftentimes the origin of that sea salt. Evaporating seawater, bringing the ions closer together. And we can have the formation of minerals upon changes in temperature and pressure on existing minerals, as seen here in the formation of this migmatite. This is a fairly high-grade metamorphic rock in which there's a slight amount of melting. Most of the minerals remain solid, but there's a little bit of melting in the case of the migmatite, and the pressure differential gives it this swirly look. Geologists and geochemists classify minerals based on their properties and based on their chemistry, based on their structure. For now, we're going to talk about the chemical classification of minerals. First up are silicates, which contain oxygen and silicon. Our example here is the mineral quartz, which has the chemical formula SiO2. Carbonates contain carbon and oxygen. Our example here is a very common mineral, calcite, CaCO3. Oxides contain oxygen and metallic cations. Our example here is the mineral corundum and in particular, this is the variety ruby. Sapphire is another variety of the mineral corundum. Very hard, number 9 on the hardness scale. We'll get back to that in a few minutes. This has a chemical formula of Al2O3. Sulfides contain sulfur and a metallic cation. Our example here is pyrite, also known as fool's gold. It commonly comes in this cubic form. It is an Fe(S)2 mineral. Sulfates contain the sulfate radical and metallic cations. Our example here is gypsum, variety selenite, from the famous Crystal Cave in Mexico. This has a formula of CaSO4 with 2 water molecules. Halides contain chloride, fluoride, iodine, and bromine. In this case, our example is fluorite, calcium fluoride. Hydroxides contain the hydroxyl radical. The example here is the very colorful copper ore, malachite. It is a Cu2CO3OH2. So in this case, the hydroxyl radical is located here, and this makes it a hydrous or hydroxyl carbonate of copper. And lastly, we have native elements. These are masses of all the same element metallically bonded. Our example here is gold.
Well, I pity the fool that makes that mistake.
Actually, this is the example. Gold. Don't be fooled.